So as the second talk of the workshop, we will have Bart Bogaerts telling us about how to do certified symmetry breaking with VeriPB. Please.
Hello, everyone. So when Jakob sent an email yesterday, he asked us to include some nice illustrations of nifty proof logging tricks. So I did what everyone does nowadays. And I asked generative AI tools to generate nice illustrations of nifty proof logging tricks, and it started to look a bit strange. Maybe symmetry breaking is better suited. So I'll talk a bit about the way symmetries are handled in SOT, specifically about symmetry breaking. And then I'll go into a lot of detail about redundance and dominance rule and how you can actually use them to do symmetry breaking. Well, I assume everyone is familiar with SOT solving and that everyone knows what proof logging is, and you're here because you're convinced that it's at least somewhat valuable. So I will focus on symmetry handling. So what I'm, and by the way, what I'm telling here is not very specific to SOT. So this is in other domains, very similar things have been done, and the ideas they carry over. So I will assume that I have some permutation of literals, and this means so I'm just think of it as renaming certain variables. And it needs to have a couple of properties. It needs to respect negation. So if I say, well, I'm mapping x to y, then I must map not x to not y. And the second thing is that if I apply it to a formula that I'm given, then it should give the same formula. And this is what it means to be a syntactic symmetry. And the syntactic is because the formula stays exactly the same. It's not just a set of solutions that's reserved, but it's actually the formula stays the same. And this is just replacing every x by a symmetry. So this is what, for me, now symmetries will be. There's more general notions of symmetries. Not all symmetries are syntactic, but in this, well, I mean, in practice, syntactic symmetries are typically what's detected. And so I'll assume to be working with syntactic symmetries. For instance, if you have this formula here, and I have this permutation that says map A to B, map B at the same time to not C, map not C to D, and swap x and y, and then implicitly, and in the gray here, it is implicitly you're also mapping all the negations of literals to the right thing, because the symmetry should respect negation. In that case, if I have that formula, if I apply the permutation to the formula, I get this. And what you can see is, so this clause gets mapped to this one. And what you can see is that this one here is exactly the one we had before, and so all the clauses were there before. So this would be a symmetry of this formula. For standard CDCL solvers, very small symmetric problems can cause huge problems for solving them. The prototypical example of it would be the pigeonhole principle, which you go up to 15 pigeons, no subsolver can solve it. Well, actually, for us, we're asking you to 15 pigeons fit in 14 holes. I think you don't need to think very long about it. So that's a bit annoying. And so if there are symmetries present in the problem, we want to do something with them. What I'm going to be talking about today, so I gave the introduction already. I'll first give a bit of an overview of different ways symmetries are handled in SOT. Jakob already touched upon them, but there's symmetry breaking, there's symmetric learning, there's more methods. I'll give a bit of an overview of that. And then I'll talk about how we're doing symmetry breaking in VeriPB. So there's something that might sound familiar here. I will give a bit details about the redundance rule, about the dominance rule, but maybe we can go slightly faster over them since Jakob already introduced them. And then I will go into a lot of details about how we actually do this. So I'll give an example with a couple of pigeons, a couple of holes, what the actual VeriPB proof looks like, how we set up this pretend optimization problem that Jakob also mentioned in his talk already. So how we're now actually doing this. And I'll talk a little bit about the challenge we recently encountered, submodulo symmetries. It's something that I thought would be quite easy to get symmetry breaking for, but then once we started looking into it, turns out that more is needed for doing this. But I'll come back to that later, and then I'll conclude. So symmetry breaking or symmetry handling techniques in general, I'll categorize them into 2 dimensions: static and dynamic. Static meaning you're getting your formula, you're manipulating it as some sort of pre-processing technique, and then you can just run another solver afterwards, or do whatever you want afterwards. Dynamic means you're doing things during search. You're exploiting these symmetries while you're searching. And then the other dimension is breaking versus non-breaking. By breaking, I mean that you're actually eliminating solutions. So you're doing things that eliminate solutions, but if your problem is satisfiable, you shouldn't eliminate all of them. Yeah? By non-breaking, I mean techniques that do not do this, that still exploit symmetries, but that don't get rid of any solutions. So intuitively, you can think of this as symmetric versions of unsatisfiable branches in the search tree you can get rid of. There's no techniques in this quadrant here. So all the static techniques that at least I know of are effectively breaking. And that's maybe not so surprising since you're doing something in pre-processing. Static techniques that are breaking, the most commonly used is what's known as global symmetry breaking. You're getting a bunch of symmetries, and typically what this will do is produce to add Lex leader constraints or some other order, but Lex leader is what's most often used. So what this means is we're adding a set of clauses such that if an assignment satisfies it, it means that it's smaller than or equal to its symmetric version. And so this here, this alpha after sigma is the symmetric version of alpha. So these symmetries, I introduced them as we can apply them to formulas, but you can also apply them to assignments. So what we're saying is we're only interested in those solutions. If we have two symmetric solutions, we just take the smallest of them according to some suitable order. Then if you go to the dynamic symmetry breaking, there's a bunch of methods here. There's local symmetry breaking. The way you can think of this is during search, you're left after making some assignments, you're left with some formula, a subformula. Some clauses are already satisfied, some literals have disappeared from clauses, and you could just detect symmetries on that as well, on what you have left then, and then add locally in this part of the search tree symmetry breaking clauses. This would work perfectly well. And that's what this local symmetry breaking refers to. So it's very similar to this, except that you're doing it during search, and maybe after making some assignments, the symmetries will become more clear. There's asymmetric branching, which is what was done in Stincha. So what they do is for very simple symmetries, basically think of it as a set of variables that's interchangeable. Yeah. Instead of just picking one of the variables and branching on it, you can branch on the whole set at once, but branch on how many of these are true, because they're all interchangeable anyway. So you can just branch on how many of them are true, and then you can just take the first k to be true and the rest to be false. That's what's happening there. Something known as effective symmetry breaking. The idea of effective symmetry breaking is we're going to do what the static symmetry breaking does, or something very similar. But there's always the question here of how far do I want to go? How many symmetries do I want to go break here? How deep do I want to break them? And so I'm saying here I said we're adding Lex leader constraints, but you can add them for lexicographically for over all the variables. It should be smaller than the symmetric version, or you could say, well, no, I'm just going to approximate it and at a certain point stop because I cannot, because it becomes too long and too large a clause otherwise. The idea of effective symmetry breaking as well. Let's implement some sort of propagator, lazy clause generation style that adds these symmetry breaking constraints on the moment that they would propagate. So basically, we're not going to add them in advance, but we're going to let the solver run a bit, and we're going to see now it would be useful for you to have this symmetry breaking constraint. So now I'm just going to add it. And submodulo symmetries and submodulo computer algebra are also similar. They also add some propagator that propagates lexicographic minimality. And I'll come back to submodular symmetries in a bit. And then there's more dynamic work, dynamic non-breaking. So this is here, and there's lots of different techniques there, but actually all of them are variants of symmetric learning, or can be viewed as symmetric learning. And the idea of symmetric learning is once you have learned a class, so your formula entails a certain class. In that case, you might say, well, if my formula entails this class, then it also entails a symmetric class. Yeah, because my formula was symmetric. So if it implies something, then it also implies a symmetric variant. So whenever your subsolver is learning new clauses, you might just add all the symmetric versions of it. But that might be a bit costly to add all of these symmetric versions. There's many of them. You're just drowning your subsolver in clauses. So the way these techniques differ is in how when exactly certain symmetric clauses will be added. And this is kind of searching a balance between adding enough clauses to make sure that you avoid lots of useless parts of the search tree, but not adding too many because you don't want to drown your solver in clauses. And then there's one technique here that's here in the middle here that combines effective symmetry breaking with this symmetric learning. The SP stands for symmetry propagation, but it's actually, well, it can be seen as an instantiation of symmetric learning. And so the reason why, why symmetric learning is not breaking is because you're only learning symmetric variants of clauses that express in this part of the search tree there are no solutions. So meaning the clause that you learn this way, the symmetric clause, is excluding a symmetric part of the search tree where there are also no solutions. So you're not getting rid of any solutions. And so this is kind of a hybrid between the two. So it will, to some extent, do effective symmetry breaking and to some extent symmetric learning. So it's a combination of the two. Okay. Now, what does this have to do with proofs? Because we're here on a proof logging workshop. So for static symmetry breaking, there has been direct proof logging for limited cases. So if your symmetries are simple enough, you can go do and not interacting too much, you can do direct proof logging for it. For the general case, there has been VeriPB based proof logging, and I should update this to the journal reference, updated 2x3, so it should be 23 now. And this idea how we're doing static symmetry breaking also appears to be applicable to dynamic symmetry breaking. We have some prototype version of the effective symmetry breaking. I thought all the other symmetry breaking methods also looks quite applicable there, but I will talk about challenges when it comes to submodular symmetries, and especially the way it's used. But that's for the end of the talk. For symmetric learning, there has been a proposal of a proof system that's very specific for doing this, where basically you have rules that allow you to see that something is indeed symmetry. And so this has an explicit concept of symmetry in the proof system. And an annoying thing is it's not very compatible with pre-processing techniques, this proof system. So it's really specified, it's really designed specifically for symmetric learning. It would be nice to have this integrated somehow into a more general framework. Okay, so VeriPB, we've seen an overview already of what it is. Summarized briefly the reasoning with pseudo-Boolean constraints. We have a cutting planes proof system, and we extend it with strengthening rules. And my focus here will be on this strengthening rules in the proof system. So pseudo-Boolean constraints, we know what they are. I didn't say too much about them. Cutting planes, linear combinations of axioms, division. I will not use this too much either. So let's skip over the details. The strengthening rules, they are about deriving new constraints. And the question is, when is it okay to derive a new constraint? If it's implied, sure, you can derive it if it's implied by what you already have, but you can go beyond that. So for instance, an example is you might want to introduce a new variable that's true even only if a certain formula is true. You want to reify a formula, introduce a new variable for it. If this variable a occurs nowhere before in your proof, I think I can convince you that I'm not doing anything wrong there by saying, well, I just make it true even only if this formula is true. It should always be possible, yeah. But clearly this is not implied because your original formula was not saying anything about a. So you need something more general. And these reifications, we will also see them coming back in the constraint programming talk, and they're used quite a lot. So what we need is some sort of without loss of generality arguments. And the same actually when I'm talking about symmetry breaking, when I'm saying, well, I'm only going to be interested in assignments that are lexicographically minimal. Well, in that case, I'm doing it without loss of generality argument, because if there's any solutions, then without loss of generality, they're always lexicographically minimal. So all of these strengthening rules are about reasoning without loss of generality. The basic strengthening rule we have is redundance-based strengthening. So intuitively, if adding a new constraint to our formula doesn't change the satisfiability status, then it should be fine to do this. But of course, this rule just saying you're allowed to add any constraint that's satisfiability preserving is not going to work, because then you could just add the contradiction immediately for any unsatisfiable formula. So you need something that's verifiable that the proof checker can check easily. And so what we're going to say is we're going to need to give witness, yeah, a witness, and we're going to prove this explicitly using, for instance, cutting planes or whichever suitable way you see it. And what's happening here is this witness here. You can look at it in two ways. Yeah, one way, this witness, you can view it as a syntactic manipulation of formulas. Yeah, just replacing every variable in F and C here by whatever omega tells you to replace it by. And so the proof obligations, they are about this syntactic view of the witness. The second way of viewing it is, as well, you can view it as a manipulation of assignments. And this is, we're going to replace an assignment alpha by alpha after omega. And the nice thing is that alpha satisfies a certain formula where all the replacements have been made syntactically, even only if the patched up assignment satisfies the original formula. So what this really tells us is that if I have some assignment that satisfies my formula but not my new constraint, then the patched up assignment will satisfy both. So it gives me a way of constructing from formulas that satisfy F, constructing formulas that satisfy F and C. This is how we can think of it. Yeah. I'm gonna skip the proof sketch here, and I'm also gonna skip this because Jakob has explained this. I have another example where we can reason with this redundance rule. And by the way, you can download the example runnable in VeriPB if you see a QR code. Then you can get the original OPB specification and the proof with some comments in there to make it clear what's happening. So let's look at this example. We're given a graph here, and I'm asking you, is this graph two-colorable? That's an easy problem, yeah. And when we solve this problem, what we do is we say, well, without loss of generality, we're just gonna color one of the nodes, and then we're gonna see what follows, and then we're gonna be able to conclude. In this case, no, it's not two-colorable. Now, how can we convince a proof system about this? Well, first of all, I would like to say without loss of generality, I can color a specific node. I can color it red or blue, whatever. Now, why can I say this without loss of generality? Because I know, well, for instance, node 1, without loss of generality, it's colored blue. Well, if it's not colored blue, I just swap all my colors. I patch up my assignment, and then I change all the blues by red and all the reds by blue. And then if the original was a solution, then the new one is also a solution. The colors are completely symmetric. Yeah? So somehow this patching up should end up in the proof. Now, if you want to do a proof, we first need to say what the formula is. And the formula will just tell us. So I have variables that tell me, so B1 tells me whether node 1 is colored black or whatever, or blue I'm using, I guess, in method. if node 1 is colored blue or not. And this tells me that for every edge we have, one of them should be colored blue and the other one should not be colored blue. Yeah, so they should have a different color. We have this for all the edges. That's what our formula looks like. And so without lots of generality, we want to assume node 1 is blue. And we're going to need some strengthening rule for that, because certainly this is not implied for colorable graphs, and we don't know yet if it's colorable or not. So what we're going to do is we're going to say, well, without a lot of generality, B1 is 1. So it's greater than or equal to 1. There's 0, 1 variables, means it's 1. And we're going to take a witness that maps every variable to its own negation. So it's touching all the variables at once, and it's swapping all the colors. Swapping all the colors at once. That's the patching up that we were thinking of. If I have an assignment, I'm just going to swap the colors. I'm going to replace all the BIs by not BIs. And now, if I want to apply this redundance rule, what my proof obligations are, I need to show that F will still hold. F will still hold after replacing every variable by its negation. And this you can see because, well, if I replace all the B's by not B's, then this constraint, the first constraint, is actually mapped to the second constraint, and vice versa. We're just swapping these two constraints. The same with these two, and so on. And what I should also show is that my new constraint that I want to learn, B1 is greater than or equal to 1, is satisfied under this assumption. So if F was satisfied and this constraint was violated, then it will be satisfied after swapping all the variables. So, but the fact that the constraint was originally violated, so I had an assignment in which node 1 was not blue, then clearly in the patched up assignment, node 1 will be blue, because this is just adding a negation. What this looks like in VeriPB is we start by saying, well, we're using this version 2.0 of the checker and the language. We're loading a formula with 18 constraints in it. Yeah? And then next we're saying we're doing a redundance rule. This is the constraint we want to derive. So 1 times B1 is greater than or equal to 1. And then after the semicolon, we specify the witness, namely map B1 to not B1, B2 to not B2, and so on. Yeah. So this line is just telling me, without a lot of generality, I can color 1 blue. And now actually we're done, because the way you check bipartiteness of a graph is you will then just basically traverse the graph. You will very easily see, once one has to be colored blue, what all the other colors have to be. And the wrap rule in this case is actually allows us to see this, since the graph is connected. So what this will do is we're saying, we're just saying here reverse unit propagation and a contradicting constraint. What this means is that what we have so far will propagate to contradiction. Yeah? And why does it do so well? We have that B1 is 1. So B1 is 1, meaning that node 1 is blue. Because of this and that constraint, node 2 has to be, is propagated to be not blue. So let's say orange, and so on. And these propagations, so all of these guys are propagated to be orange. And then these two guys are propagated to be blue by the right clauses, all binary clauses, all propagating very well. And then we have a contradiction here. Yeah. So this is really just the traversal of the graph that's happening, but now it's happening inside the unit propagation. And then we end the proof by saying, well, this was not a proof of a translation or anything. There's no outputs. The conclusion is just that the input was unsat, and that's the end of the proof. In the optimization setting, for now, I was talking about decision problems.
Sorry, I got a question.
Yes.
When we do the swapping, why do we do only the positive literal to the negative one and not the other way around?
With these, in these witnesses, you only specify the positive literals, and then no.
The substitution is on variables, right?
The substitution, yeah,
substitution always maps variables.
Okay.
You can also think of it as mapping literals, but I mean, this, for instance, if I have a literal not B1 somewhere in the formula, then this will be mapped to, well, the variable will be mapped to something else, and then the double negations disappear also. So implicitly, mapping variables allows you to map literals, formulas. Okay. So in the optimization setting, we need to be slightly more careful if we want to do this. We don't just want to preserve satisfiability. We want to preserve the optimal value as well. So what we need to do is we need to make sure that our patched up assignments will be at least as good as our original assignments. So this witness is telling us how to patch up assignments. And we get one extra proof obligation here that tells us, well, my patched up assignment needs to be at least as good. And in the case that this omega strictly improves the solution, and this is also, Jakob has also illustrated this already, then we can go a bit better, and then we can drop some proof obligations. Because what this is now saying is, well, if I have an assignment that satisfies my formula, but not my new constraint, then my patched up assignment will satisfy the formula and will be strictly better. And it might or might not satisfy the new constraint. I don't care about it anymore. Because if it doesn't, I can patch it up again and patch it up again and keep on doing this. And since we're in a finite setting, only finitely many assignments, at some point, I should find one that does satisfy C. This cannot go on forever. So if the witness, so the patching up strictly decreases our objective value, we're minimizing that, then we don't need to show that the constraint still holds after patching up. And we can go, okay, so this argument I gave, and we can go a bit further than this, namely, and this is the D set from Jakob's slides here, all the previously derived constraints, basically you also don't get any proof obligations on them with dominance. As long as you can strictly improve your objective, you only have proof obligations on your core set of constraints. And think of this as your original formula.
But it's worth pointing out that, which I didn't say also, that you can use them when you establish the other proof obligations. So
yes,
it's amazing. You can use them on the left or no obligations on the right, like free lunch.
Mm-hmm. Absolutely. So this can be very powerful. So you've derived them, so you can use them wherever you want, basically. But within the dominance rule, and this is only really when you're strictly improving on your objective, you don't get proof obligations on anything you've derived so far. So this also means, and that we're really going to use when we're doing symmetry breaking, is that two applications of dominance can be done completely independent. If I do a dominance rule and I derive something, it ends up in my derived set, and then I want to do a dominance rule again, I don't care that I did the other one before. Well, I can use it, so it can only help me, but it can never hurt me that I did it before. We're doing without lots of generality reasoning, and somehow we're able to do this independently from one another, which might sound suspicious, because if I say without lots of generality, some variable a that I've never seen before is 5, and later I say without lots of generality, this variable a that I've never seen before is 7, clearly I shouldn't be allowed to do both of them. Yeah? But what this objective is giving us, it's a way to coordinate this. Namely, both of my without lots of generality statements should strictly decrease the objective. Yeah, and my argument, my example with the ace is never going to do this. But both of them are strictly decreasing the objective by fixing a to that specific value. So this is there as some sort of coordinating role between the different applications. So I'm not going to give the proof of why this works. Let's go back to symmetry breaking. So what I promised is I was going to show how to do symmetry breaking for subsolving static symmetry breaking. And the first step to do symmetry breaking is we're going to pretend to be solving an optimization. Of course, I still need to show you how we can convince VeriPB that we're suddenly pretending to solve an optimization problem. But intuitively, if you're asking me if a formula is satisfiable, yes or no, and then if I can show you that, well, this variant of it that just has an extra objective is unsatisfiable, yeah, then clearly my original formula is also satisfiable, right? Unsatisfiable. So this should be fine. If I want to show that a certain formula is unsatisfiable, I can just add an objective and then pretend that I'm optimizing something, and then use it. And this objective, what it's saying is, well, this is really a lexicographic order. It's saying that the variable x1 has a very heavy weight that can never whatever you set the other variables to, you can never beat this weight. X2, half of that weight, and so on. So this is an exponential encoding of a lexicographic order. So this is, if I'm minimizing this objective, I'm really looking for lexicographically minimal solutions. Yeah, and I'm going to prove that there are none. That's the eventual goal. And if there's no lexicographically minimal solutions, there's no. So what we're going to do when we're doing symmetry breaking is the first thing is we're going to derive the Lex leader constraint in a pseudo Boolean version. And what this says is, well, my objective value should be smaller than the objective that my symmetric assignment has. So if I'm given a symmetry, which might have been detected before, then this constraint is telling me the objective value of an assignment is smaller than or equal to the objective value of its symmetric version. And you can work this out, what this looks like in pseudo Boolean notation, something like this. And this we're going to do with the dominance rule. We're going to use the dominance rule to derive this constraint. And we're going to do this for multiple symmetries. We're going to do this independently for these multiple symmetries. So this talk is not about how to design a good symmetry breaker. This talk is about, once you want to do symmetry breaking, how can you certify it with VeriPB? Yeah? And so if for some reason the symmetry breaker decides I'm going to derive Lex leader constraints for sigma, then we can derive this pseudo Boolean version of a Lex leader constraint with one application of a dominance. And next, what we're going to do, because we're in the context of subsolving, and subsolvers like clauses, we're going to learn a lot of clauses that that actually encode this Lex leader constraint in CNF. Yeah? And of course, we still need to prove something. And what we're going to prove is that these clauses, you can actually derive them from this pseudo Boolean Lex leader constraint. And these clauses, from now on, I'm going to write them like this, not like clauses anymore, but same as pseudo Boolean constraints, but that's just the same thing. The subsolver will see the clauses. And so this works. We're participating with this in the sub competition. I guess we're one of the only solvers who's allowed to do symmetry breaking in the sub competition, unless there's more participants using the VeriPB checker this year. Who knows? Let's go to the details. So we're going to apply this to a pigeonhole problem. This is a prototypical example of something symmetric. And what I'm going to assume is I've got 4 pigeons and 3 holes to keep it manageable, to keep it make it fit on a slide. And I'm going to focus on pigeon symmetries. I'm going to ignore the symmetries of holes for now. For some reason, my symmetry breaker has decided to break the pigeon symmetries. For instance, the symmetry, this symmetry here swaps pigeons 1 and 2 is what I mean by it. And that means that in every variable that talks about, so in every variable Pij where I is 1, it will map it to the P2j with the same j. And so it will replace all the 1s by 2s and all the 2s by 1s in the first place. This more complicated symmetry, sigma 1 to 3, 4 shifts all the pigeons 1 hole. Maps 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. So it basically moves all around, moves all of them around. And our order will be pick the smallest possible hole for pigeon 1, and then the smallest possible remaining hole for pigeon 2, and so on. So I've chosen my lexicographic order in such a way that it's basically telling us we prefer to put pigeon 1 in a very small hole, and if that's not possible, well, then maybe in another. So we prefer to put pigeon 1 in hole 1. If that's not possible, maybe in hole 2, that's a bigger cost, or maybe in hole 3, an even bigger cost, or maybe we prefer to not put any pigeons in holes at all. That's a bit, then the objective will be 0. Yeah, but if we have to put the pigeon somewhere, pigeon 1 in the smallest possible hole. So I'm going to assume that F is a formula expressing these pigeonhole constraints, and that it's that this sigma 1 2 is a syntactic symmetry of it, which is usually the case, unless you do a very strange encoding. And what the first thing we want to do is we want to add this constraint that breaks the swapping of pigeons 1 and 2. Yeah. And so we want to derive this constraint, and there's this is written out in pseudo Boolean notation. So what this constraint is telling us basically is pigeon 1 is in a smaller hole than pigeon 2. That's the constraint that breaks the swapping 1 and 2 with the specific lexicographic order I've chosen. To do this, we can use the redundance rule. So in the end, I'm going to come to dominance, but to derive this, we can use the redundance rule, because when we fill everything in, what it says is that, well, if f is satisfied and the pigeon 1 is not in a smaller hole than pigeon 2, basically, then I should still, I claim that f is still satisfied after swapping two pigeons, obviously, because, well, the formula was symmetric, so this is just the same as f. Yeah? And that pigeon 1 will be in a smaller hole than pigeon 2, and that my objective is at most this. Yeah, but actually notice that so my objective after swapping it is at most what it was before. But notice that this constraint here, yeah, and this constraint are actually just the same. So if you look at it this way, how C12 was defined as f being smaller than or equal to its symmetric counterpart, yeah. If we then apply the symmetry again to it, this just becomes that. So the symmetric version of f smaller than or equal to f, which is implied by this one here, the fact that they were not in a smaller hole. So what this is saying is, if f was satisfied and pigeon 1 was not in a smaller hole than pigeon 2, then after swapping them, pigeon 1 is in a smaller hole than pigeon 2. Yeah, and this is good. And for our lexicographic order, clearly we're only improving it by putting pigeon 1 in a smaller hole. And so this works with the redundance rule. And what I explain here is very similar to how symmetry breaking works in DRED. I'm taking some shortcuts, but this is close to what they're doing. The problem with that is it doesn't generalize. It doesn't work if you want to break two symmetries, because if you want to break a symmetry that solves pigeon 1 and 2, and afterwards you want to break a symmetry that solves pigeons 2 and 3, then you kind of get into trouble, because you get proof obligations. Remember, we're doing redundance, where you get all your previously derived constraints give you proof obligations that might no longer be satisfied once you swap pigeon 2 and 3. If pigeon 3 was in a very small hole, and pigeon 1 was in the smaller hole than pigeon 2, and then I suddenly swap 2 and 3, then it might no longer be the case that 1 was is in the smaller hole than 2, because 3 was in a very small hole before. Yeah, so we have some problems here. So this doesn't just generalize. There are in DRED, they have some ways of working around this for very simple symmetries, but the idea itself needs work. And intuitively, you might have to apply this first symmetry again, swapping pigeon 1 and 2 again, now that pigeon 3 comes in the loop. And also for complex symmetries, it doesn't work. So if we have this symmetry that shifts all the pigeons by one place, then intuitively what goes wrong is your patching up is not applying the symmetry once, yeah, to get pigeon 1 in the smallest hole, but applying it once or 2 times or 3 times. Yeah, so you might have to apply it multiple times to move all the pigeons one spot multiple times until pigeon 1 is in the smallest hole. And in your witnesses are very simple. You cannot say, well, apply this to fixed point or whatever. Yeah. This is where the dominance rule comes in. And remember, this is the symmetry breaking constraint. And with the dominance rule, it becomes quite easy. Namely, you can just derive this with the symmetry as a witness. And what you need to show is this. That in that case, for a dominance, that your formula, and so if you have an assignment that satisfies your formula, and your symmetry breaking constraint is not satisfied, then after applying sigma, the formula will be satisfied, and it's strictly improving. Yeah. Now, the fact that this is not satisfied and it's strictly improving, if you look at the definition of what the symmetry breaking constraint was, that's just exactly the same. Yeah. This here is just a negation of that. Yeah. So this is just straightforward application of dominance. It works immediately. And the beautiful thing is that it generalizes to multiple symmetries, to complex symmetries, because you don't have this proof obligation on the right anymore. Yeah. So if you say I want to do another symmetry, my proof obligations that I'm getting, they completely ignore whatever I've derived before. This is in the derived set. I don't get proof obligations on this. So a second application of symmetry breaking, I just get the same obligations as I would have had the first time. Yeah. Also for complex symmetries, arbitrary symmetries, it works because I no longer need to show that after applying the witness once, my symmetry breaking constraint will be satisfied. All I need to show is that applying the witness gives me something strictly better, gives me something decreasing. Yeah. So and that's where this power comes from. So in summary, our witnesses, applying the witnesses or patching up the assignment does not need to satisfy all the derived constraints. All we need to show is that with some fixed order, we're getting better and better and better by applying them, and that's sufficient, strictly better. So let's go back to sub-solving. This, we've now seen how to do it, this step 2, how to derive, how to apply the dominance rule to derive it. It's a straightforward application. You basically don't get any proof obligations. We need to do more stuff in order to get this to actually work because we need the actual clauses. We need to derive the actual clauses. Yeah, so we need to derive this CNF encoding. I'm going to be using the encoding that we use in Breakit, and I'll quickly explain the intuition behind these clauses, what this actually means. So what we're doing is actually there's some definitions in here. I'm defining a variable to be true in certain cases. And these are the y variables. These y variables, they're fresh. They don't occur anywhere else in my formula. They're fresh variables. And I say that yj will be true if up to point k, for all k's below, up to point j, for all k's below j, the variable equals its symmetric version. Meaning that if I'm comparing an assignment and its symmetric version lexicographically, they're the same up to point j. This is what yj means. And how do we define it? Well, you could define it like this, saying okay, I have a k here. It might be confusing, but okay. So you're equal up to point k, even only if you're equal up to point k minus 1, and at exactly point k, you're the same. This is what this is. And then all these clauses, these orange clauses, are a compact way of encoding this. Yeah, you could just work this out and get other clauses out of it, but these ones here are compact. For instance, what they're saying is if you look at this one here, it's saying if yj is true, then yj minus 1 also has to be true. So this is part of the implication to the right. Yeah, and this one here, y0 is just always. It's for for doing this nicely. In general, you could also just replace this by 1. You don't need to introduce this. And these we're all going to derive with the redundance rule. Yeah, and then this one here, the black one, now green. Yeah, what this one is telling us, it's telling us that if yj minus 1 is true, so if the assignment and its symmetric counterpart are equal up to point j, yeah, then at point j, xj can be at most sigma of xj. So meaning we're comparing two assignments, they're equal up to a certain point. Yeah, one should be lexicographically smaller than the other. So at this point j, this can be at most that. So if yj minus 1 is true, and there's greater than or equal to 1's missing here in my slides. So imagine there being greater than or equal to 1's here everywhere. Yes?
So why is it that you need to derive the CNF encoding of your Lex leader rather than just relying on the PB constraints that you already introduced?
Because our subsolver is going to be using the CNF encoding and to be learning clauses with it. So the idea is we're doing symmetry breaking and then running a subsolver afterwards, and the subsolver only understands the clauses.
Yeah.
So this is what the tools are actually producing, the CNF encoding, and the PB encoding of the pseudo-Boolean of the Lex leader constraint is just, well, something intermediate that only lives in the proof, but the subsolver doesn't speak the language, doesn't understand this.
Yeah.
Okay, so what this is saying is if yj minus 1 is true, so they're equal up to j minus 1, and xj happens to be true, then sigma of xj should also be true. So let's do this in details in a proof. We start our proof as usual, we load our formula, And now there's this huge block here that's about pretending to solve an optimization problem. And what we're doing here is we're doing something slightly more general than just an optimization problem with a linear objective. What we actually allow is to specify an order between assignments. Yeah? So we're going to order our assignments. Yeah? And the way you can think of this is, well, I'm going to be comparing two assignments. And I will need this in my dominance rule to show that whenever I apply it, it gets, after applying the witness, my assignment gets better and better, lower and lower and lower according to this order. Yeah. So what we say here, well, our order looks like this. I will, in this case, it's the one I showed you before. But we will have variables on the left and variables on the right, and you can think of this as variables of the first assignment and variables of the second assignment, the corresponding variables of the second assignment. Yeah. And what we're defining here in the define statement, we're giving you a formula, and if it's true, it means that the first assignment is smaller than or equal to the second. This is what the formula being true means. So here, this is just one constraint, but this could be many constraints. When we specify such an order, we need to prove some things about it. For instance, that this is indeed transitive, and there needs some proving inside VeriPB to show, well, the order I'm giving you is a decent order. I'm not just writing an arbitrary formula here, and I'm well, actually doing something right here. So, and this part here of the proof tells you, well, we're going to prove transitivity. To prove transitivity, intuitively, we need a third assignment. So we introduce, again, fresh variables here. And then we give the proof of transitivity. And because it's just a very simple one-line order we're defining here, it's a short proof. Yeah. At the very end, we say we're now going to load this order. And specifically, and now we're going to say, whenever we want to compare assignments to which a witness has been applied, these are the variables of the actual formula we're going to fill in. Yeah. So what's going to happen if we want to check whether one assignment is smaller than or equal, so whether the patched up assignment is smaller than or equal to the actual assignment, we're going to have to prove that for any value of these variables, if I fill them in on the right, where the v's are, or I fill their patched up version in on the left, then I get something smaller than or equal. And it cannot be the other way around. So if I want to show strictly smaller, it cannot be the other way around. So I will have two proof obligations with respect to this order. So this is the magic you need to do for setting up this fake optimization problem. This can even work in the context of real optimization problems. So you can have real optimization problems and apply dominance there, where you have your actual objective, and then you define a separate order that you promise that you're going to be strictly decreasing in whenever you use dominance. And then we're going to derive the constraints. So the first thing that we need to do is we apply the dominance rule, and this here is just saying our pseudo-Boolean Lex-Wheeler constraint that we had before. So this is the C12 I called it before, and here behind the semicolon we've got the witness specified. When I explained this, I said basically we have no proof obligations. Everything is obvious, except that there is one proof goal that we're getting, which is basically saying that one constraint is the negation of another constraint, or okay. So it's one of these things where we had almost exactly the constraint on the left or on the right, and VeriPB cannot see this automatically. So this was a bit annoying, you could say. But the only thing we need to do here is we're gonna, so this is the witness. What we need to do here is show that not C12 and C12. Okay, so now this is what we have to show. We had a constraint and its negation in the database, yeah, and we needed to show that from this contradiction follows, yeah. For us, this is obvious because VeriPB doesn't see that one constraint is a negation of another constraint. Yeah, you need to tell it, and cutting planes gives you a very simple way of telling this, namely add up these two constraints, and you will get a contradiction. Yeah. So the way we show these things is we say, well, if f is true and not c12 is true, we need to show that this holds. The way we're actually showing this inside the proof system is adding the negation of the orange thing to the left. And this is just c12, and then we should derive a contradiction. And the -1 and -2 here refer to, so this is reverse Polish notation. It tells you take constraint -1, so meaning the last constraint you've derived, and constraint -2 and add them up. And this QED tells us, well, the last constraint I derived now, which is the one here, is actually a contradiction. Yeah. And then we're going to be deriving all the clauses. So now we're done with the breaking constraints. So now we can start deriving the clauses. The first one is easy. This is just telling us why 0 is true. That's the easy one. We just use the redundance rule and basically after filling in this witness, clearly this is with witness y0 being mapping to 1, and clearly this will satisfy it. Yeah, and it's a fresh variable, so it doesn't interfere with any of the clauses so far. And then we're deriving this constraint here. This is the actual breaking constraint at the first place, using RUP, reverse unit propagation. The idea is now this breaking constraint follows immediately from the pseudo-Boolean version, because what this is telling us is basically that the dominant term of this this is telling us something about the dominant term of this formula. So the term, so the places where you have this 2048, so the big numbers in there. Yeah. If you fill in reverse unit propagation, if you fill in the negation of this constraint, if you assume the negation of the constraint, so you assume that y0 is true, that p13 is true, and that p23 is false, and you fill this in the derived constraint, then you will get an obvious contradiction. Yeah. So this is how we derive the actual breaking constraint. How am I doing on time?
Well, a few more minutes.
A few more minutes. Okay. And then we go to the next wise. What we're now going to do is we're gonna. I said these y's are defined in terms of the previous y's and the last value. So remember, yk means being equal up to a certain point k. Yeah. And here we can just use the redundance rule. This is just reification that we're using. We can just use the redundance rule to derive all these y's. Yeah. And after doing that, something else is happening here. And what this is telling us now is take your previously derived pseudo-Boolean breaking constraint here and basically delete the dominant term from it. So add up 2048 times the constraint that I have just that I've derived here, one of the previously derived constraints. And what this gives you is something very similar to what you had before, except that your dominant term has disappeared. Yeah. And then you will do this for the next term, and everything will be, and then your breaking constraint will be RUP again, and you can introduce the new y sense. So you continue for all the next variables. Yeah. So this most of it follows in the obvious of these clauses follow in quite an obvious way, namely wherever we're introducing fresh variables, we're using the redundance rule. And we're only witnessing in these redundance rules on these fresh variables. This is the way we're doing reification. And there's one place where we needed some more work. We needed to be slightly more careful. And this was getting the actual breaking clause, so not just the definitions, but the actual breaking clause. But this could just be wrapped under the condition that we always simplify our pseudo-Boolean breaking constraint, and once we've established that the first term has to have a certain value under the condition that they're equal, we just get rid of this dominant term. So this dominant term has here been replaced by the if they're equal to a certain point. So this actually, that Megan mentioned, the pseudo-Boolean constraint now becomes if they're equal to up to 0.1, then break from 0.2 onwards. This is the intuition that's there. And this, if you're equal up to 0.1, will then be carried along inside the next clause. Okay, now let's take a step back. So we've seen a lot of details about how to do symmetry breaking. And in previous talks, I claimed, well, for all these dynamic symmetry breaking methods, this works well. And of course, if I start with such a sentence, then it's usually followed by an however. We started looking into detail in submodular symmetries, and there are a couple of annoying challenges. So I'll tell a bit more about why it exists, submodular symmetries, and the way it's used is that mathematicians often want to generate all objects of a certain form. For instance, all graphs of a certain size, or all graphs with very specific properties of a certain size. But mathematicians are not interested in objects themselves, but in objects modulo isomorphisms. So all graphs of a certain size with certain properties, modulo isomorphisms. And so the idea of submodular symmetries is, well, let's encode on the one hand our problem of being a graph with certain properties of a certain size, and on the other hand, we know what the isomorphisms are of these kind of objects. Yeah. So let's devise a propagator. It's very efficient for this kind of specific kind of things, and it propagates the lexicographic amount. And the first idea is, well, whenever the propagator wants to learn a clause, a lex leader clause, we can just do exactly what we did before. Because it's just a lex leader clause, we know what the symmetry is, we can just apply it. Yeah? And this is possible, but there's there's a couple of challenges. First of all, the mathematicians are not just interested in, are there any graphs of size 10 with these properties? Sometimes they're interested, but often they're also interested in all of them, in having the actual set. And how can we prove that we enumerated all of them? Another challenge is that the isomorphisms, they might not be symmetries of the subencoding. So because the encoding might be asymmetric, you might have to count somewhere and use some totalizer tree where you've arbitrarily chosen how to organize your nodes, and your encoding might not be asymmetric at all. So how can you then prove that you're allowed to do symmetry breaking with this isomorphism if it's, I mean, it requires a lot of tinkering, I guess, to get this to work. But another challenge is, so what we've been proving until now is soundness of symmetry breaking. You're allowed to derive these constraints. But what the mathematicians also want is, they don't want duplicates in their enumerated set. They want the symmetry breaking to be complete, so that they only have one representative of all the isomorphic graphs of a certain satisfying this property. So how can we verify this? And I think if we want to do this, this requires significant changes to the proof system, because we will not be able to get around. It should be specified as part of the input what the isomorphisms are we're interested in. If we really want to certify this, the set of isomorphisms should be part of the input. The proof system should know that you want to generate solutions modulo these specific isomorphisms, because you cannot derive them from the encoding.
Yeah, we're back at it. Yeah, we're back at 1.
So wrapping up, so I've talked about a variety of symmetry handling methods for static and to some extent dynamic. We have some working version that just checks the soundness for submodular symmetries, and we have a version that works for effective symmetry breaking. So for static and to some extent dynamic symmetry breaking, we know how to do this in VeriPB. A challenge could be to get this to work in Direct as well. We don't know if it's possible. We haven't seen it. We're constantly using the dominance rule, but this rule hasn't been studied in the proof complexity world, or it seems to be very convenient, but theoretical properties have not been analyzed yet. For dynamic symmetry breaking methods, this submodular symmetries is a big challenge. There's other methods, but they all seem to be doing something similar to lexicographic leadership. So that shouldn't be a problem. But with the submodular symmetries, the question is really, how can we? It's an open question. What should proofs even look like that certify that we've generated exactly one representative of each clause? For symmetric learning, it might be nice to do this in a more in a formalism that doesn't need to know about the symmetries, just like VeriPB doesn't need to know about the symmetries. All we're giving it is a way to batch up assignments in a certain sense, and it's turned out to be very convenient. And proofs with lemmas might be useful there, but getting this to actually work in practice seems to be a challenge. I'm hiring postdocs. I mentioned this already. ERC project starting in October. So if you want to join KU Leuven, let me know. There's lots of useful pointers here, the VeriPB format, description of VeriPB, and all the examples from this talk that you saw, and also several examples from our tutorials can be found here. So the VeriPB file, the OPP files, with some comments about the details that are going on. Thank you.
We should head off for lunch. Just one quick question, maybe, as people are also waiting to get the room because they messed up the booking bit. Are there any questions? No quick questions. No. Okay, let's take the questions then after lunch. Let's thank Bart again.